In this video, we're going to talk about writing the idea of general even and odd numbers in the language of algebra. Now, we all know even numbers. What does a number mean to be even? Well, even numbers, of course, they're whole numbers. And you can either say that are divisible by 2 or have a factor of 2. Any of that language is good, but I'm going to say factor. So whole numbers that have a factor of 2. And we're going to talk about factors more in depth later in the course, but a factor, for example, we know 10 you can write as 5 times 2. So 10 has factors 5 and 2. Since 2 times something gives you 10, 5 times something gives you 10. So that means that 2 and 5 are factors of 10. And 10 is even since it has a factor of 2. And odd numbers, probably the easiest way to write that, they're whole numbers that are not even. And let me clarify whole numbers here. So when I talk about whole numbers, I'm talking about numbers like our counting numbers including 0. So 0, 1, 2, 3, 4, 5, 6, all the way infinitely far. So that's what I mean by whole numbers. Again, a little bit later in the course, we'll talk about different number systems because a bunch of them will come up, and we'll come up with some nice notation so I don't have to keep writing whole numbers or counting numbers or fractions over and over again. So we're going to come up with some nice, we'll call it set notation a little bit later. But we know what even numbers and odd numbers are. So let's explore the concept just a little bit. So even numbers, of course, well, an example of one is 6. And 6 is even since you can write it as 2 times some number, 3, whatever. Really, whatever number this is isn't important to the fact that it's even. The only bit that's important to the fact that 6 is even is that 2 is a factor. Another even number is something like 12. I can write 12 as 2 times 6. Since I can do that, 12 is even. And again, the 2 is the important number. The 6 we can think of as just like some other number. So let's draw these in diagrams a little bit. So I can write 6 as 2 dots by 3 dots. So 2 by 3. So I can have a little rectangle there with 6 dots. It's 2 dots by 3 dots. 12 I can write as 2 by 6. 2, 3, 4, 5, 6. So this is 2 by 6. And if I say that I have a number n, if I say n is an even number, you know something about it. Well, that means that I can write n as 2 times some other number. So I can express n in terms of, in fact, since I'm saying it's some other number, let me give it a name rather than just a blank here. So let's call that other number, I don't know, how about k? And I can visualize it with dots like this. So I don't know what n is, but I definitely know I could write it as a rectangle of dots where one dimension is 2 and the other dimension is some number, whatever number it is, k we'll call it, since 2 times k gives me n. And every even number can be expressed like that. This is kind of the, you can think of this as the blueprint for even numbers. Great. So if this is the blueprint, let's write that down. So this is a very important note. All even numbers let's say n can be expressed as n equals 2 times k for some whole number k. And I better tell you that we're still dealing with just whole numbers here. So even whole numbers, n. So whatever you like, you can express an even number as 2 times some other number. So, quick example, just to make sure we get this. 104. 104 I can express as 2 times some other number, and that number is 52. So in the case of 104, this some other number, this k, is 52. So whenever we want to write down a general even number, we can write it down like this. We can say, well, it's even, so we must be able to express it as 2 times some other number. That's the key for this section. And now that we've dealt with even numbers, we're going to deal with odd numbers next. For odd numbers, well, let's do some examples and see if we can figure it out. So, we know 5 is an odd number. Let's do it with dots first. Remember, it's not even. So that means, if I draw it out in dots, I'm not going to have a full rectangle. I'm going to have one guy here left over. So I have this bit's a rectangle, but if I put them in groups of 2, I'm going to have one left over. So I can look at this as you have this 2 by 2 rectangle with one more left over. So I can express 5 as this 2 by 2 rectangle with this dot left over. If you have a number like 11, well, same idea. Let's draw 11 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can see we don't have a full rectangle. It's an odd number. We have this kind of dot just hanging out in no man's land, not having a full row here to make a rectangle. But every other row is full here. So it's basically an even number, 2 times 5. It's like 10 plus an extra 1. So we can write 11 as 2 times 5 plus 1. So we can think of this as an even number plus 1, the even number below it plus 1. So in general, if n is odd, we can write n as 2 times some other number k, but with that extra 1 left over. So let me just draw a little diagram here to illustrate that. So let's say we have this 2 by k rectangle. We have k rows of 2 dots each. But we have this extra 1 left over. So, in general, every odd number can be written as 2 times some number plus 1. So again, let's do something like 97. Well, 97 I can write as 2 times 48. So 2 times 48 is 96 plus 1. So all I'm doing in some sense is I'm just grouping 97 dots in groups of 2 as much as I can. So if I do that, I get 48 rows of 2 dots each, but that's only 96 dots, and there's this 1 guy left over. So all odd numbers can be written as 2 times some number plus 1, or an even number plus 1. So that's our next note. All odd whole numbers can be written as, actually let's call the whole number n. So it can be written as n, which is 2 times some other number plus 1. And I introduced this variable k, so you should, whenever you introduce a variable, it's a good practice to tell people what that variable is. So where k is another whole number. So we know how to write a general even number, and we know how to write a general odd number. So let's deal with this, and let's see if we can do some algebra with these. So here we have 4 expressions involving even and odd numbers. So let's see if we can translate these into algebra, and we'll simplify them a little bit just to kind of see some nice properties that are going on here, and we'll deal with this more and more as the course goes on. So the first one is an even number squared. Okay, so let's do that. So we need an even number, so let's call n will be our even number, and we want to write n squared, but if n is even, I can write n as 2 times k for some whole number k. So if n is 2 times k, since n is even, so knowing that n is an even number, I can write it as 2 times k. Again, there's nothing special. I used n and k again because I talked about them in the last slide, but you could use different variable names if you like. There's nothing special about n and k. So I want to write an even number squared, n squared. So you could think you're done, but let's simplify this. We know n is 2 times k, so this is going to be 2k squared. So this is 2k times itself twice. That's what an exponent means. Take what's in the base and multiply it by itself, exponent number of times. We're going to take 2k, multiply by itself twice. So we get 2 times k times 2 times k. And remember, multiplication, we can just move things around how we like. So 2 times 2 is 4. So we have 2 times k times k. And k times k we can write as k squared. So that's great. So we wrote an even number squared and simplified it to get 4 times k squared, which is fantastic. So that was 1. Now try to do it for number 2 now. Do an odd number squared. Pause the video. See if you can write down and simplify an odd number squared. All right. So again, let's use a different letter. I'm going to use M just to make things a little different. And I'm going to, instead of K, I'll use A, I guess. So 2 times some number A plus 1. I know I'm looking for an odd number, so since it's odd, I should be able to write it as 2 times some other number plus 1. And I'm naming that M, and since I introduced what A was, I should tell people. So A is just some number for some whole number. For some whole number A. Okay. Now, M squared in this case, well, M is 2A plus 1 squared. So, again, let's multiply that out. So we get 2A plus 1 times itself twice. And we're going to use the distributive law. So we're going to multiply every term in the first bracket by every term in the second bracket and add them all together. So 2A times 2A, 2A times 1, then 1 times 2A, 1 times 1, add them all together. 2A times 2A is 4 times A, so 4A squared. Then 2A times 1 is 2A. 1 times 2A is 2A, and 1 times 1 is 1. So these two were 2A times 2A plus 1, and then these two were 1 times 2A plus 1. And then we can simplify this, combine our like terms. We get 4A squared. 2A plus 2A is 4A plus 1. So that's great. And as a little aside before we go on, let me talk a little bit about this distributive law. You've probably heard of it called FOIL, and that's great for when you have only 2 terms. But if I explain kind of what's going on pictorially, it's a little bit easier to see how to generalize this and how you can just do the same procedure for any number of terms in each bracket. So if I look at this as 2A plus 1 times 2A plus 1, so let me write that as a rectangle. We're multiplying, so we can think of this as a rectangle. So this is, it's going to have dimensions 2A plus 1 and 2A plus 1. So I'm going to break it up as 2A here and then 1 here. So the whole length is 2 times A, whatever A is. A is some number, that's fine. So it's going to be 2A here and 1 here. And I'm going to do the same thing here. I'm going to break this up as 2A and 1. So the area of this whole rectangle is 2A plus 1 times 2A plus 1. But I can calculate this area in pieces. I can calculate it as the area of these 4 rectangles added together. And that's the whole idea of the distributive property. So this rectangle here, it should look more like a square since it's the same dimension. In fact, both of them should look like a square. It's not the best drawing, but that's okay. So this rectangle has area 2A times 2A, which is 4A squared. So that's that bit, 2A times 2a is 4a squared. Then this rectangle is 1 times 2a, which is 2a. This rectangle is 2a times 1, or 2a by 1, which again is 2a. And then this rectangle is 1 by 1, and 1 times 1 is 1. So you can see that each of the pieces here, 4a squared, 2a, 2a, and 1, represents one of the pieces that we broke up our rectangle into. And you could imagine if you had 3 things up top rather than 2, maybe you had something like 2a plus b plus 1 or something like that, rather than just breaking up into 2 chunks vertically, you'd break it up into 3 chunks. And same with this dimension. That's all that's going on when you're doing the distributive property. But anyway, that's just a little aside, but we did get our final answer, 4a squared plus 4a plus 1. Let's do 3, and then I'll get you guys to do 4 by yourselves, and you can check it afterwards. I do want to talk about 3 because we have 2 even numbers, and we have to be careful. So if we have 2 even numbers, let's call them m and n are going to be our even numbers. And I do want to stress a point here, and it's a very important point. So you could say, well, they're even. All right, so m is going to be 2 times k. And a lot of students will write, well, n is also even, so that's going to be 2 times k. But remember, k is a variable. So once you pick it, if you pick a number to stand in for k, well, it's always going to be that number in the expression. But m and n could be different even numbers. So since these could be different even numbers, imagine, for example, that we had, say, 10 and 8. So 10 is 2 times 5, and 8 is 2 times 4. So of course, these guys are different. So if they could be different, well, we just need to pick a different letter. We just can't use the same letter twice. So that's the big important thing here. Because m and n could be 2 times different numbers, I have to use different variables. Maybe I'll use L to mean that other number for n. So that's the big takeaway. I have to use, because they're different numbers, I need to express them using different variables. Okay. So let's go ahead and do it. So we want the sum of 2 even numbers. Our even numbers are m and n. And it didn't tell us what even numbers to pick, so we can't use examples, and we'll talk about that a little bit later in the course. We have to do this in general. So m plus n, well, m is 2k and n is 2l. And if we want to simplify this, well, I notice that both of these terms has a factor of 2. So I'm going to factor out the 2 from both of those terms, and I'm left with k plus l. And if you think about that, what is this saying? Well, this is saying if I add m plus n, I end up with 2 times some number. Look at this. K plus L, both of these guys are whole numbers. K plus L is a whole number. If you add 2 whole numbers, you get a whole number. So what does that mean? So that means this expression, m plus n, is even. Since I was able to write it as 2 times some whole number, well, that means that it's even. And you can kind of see that pictorially as well. Let me draw that pictorially. So here is going to be m. So m, we said, was 2 times k. So it's k rows of 2 dots each, and that is our number m. So I'll circle m in red, and then I'll do green for n. N, and I'll just put it at the bottom. I'll glom it on. So that's 2 by L. So it's going to be L rows of 2 dots. So that is the number n. And I just put, just to be clear, I just put some dots here because I don't know how many rows to draw, because k and L are not fixed numbers. They can be whatever number you like. So just to indicate that, I said, well, we don't know how many we're going to draw, so we'll put some dots just to get the idea across. That's fine. But if I look at the numbers m and n added together, that's like just glomming these rectangles to make one big rectangle. So this m plus n, which I'll do in blue here, that's this guy. So it has still 2 dots in each row. And how many rows does it have now? Well, it has k rows here and L rows here. So in total, it has k plus L rows. So that's all that's happening when we look at it algebraically. So if we have this 2k, that's the red bit here, and 2L is the green bit, that's m and n. And then we can glom them together to make one big even number, m plus n. And if we do that, we get this 2 plus k plus L. So, in fact, what we've done here in some sense, and we'll do this in more detail later in the course, but we've proved a result. That's kind of cool. So the result that we've showed is that the sum of any 2 even whole numbers is even. So that's great. And we've shown this for any 2 whole numbers. Remember, m and n are blueprints for any even whole numbers that we like. So this works for any whole number. We can't just do examples, because then we're just showing it works for those particular examples. So that's great. So let's just do 4. We're going to talk about this idea, of course, more in the course a little bit later. And 4 is the product of, let me scroll back up so you can see it. It is the product of an even and odd number. So again, pause the video now, try it yourself, see if you can come up with a good way of writing it and a good way of simplifying, and we'll go from there. Okay, so we want one even number, so m will be our even number, I guess. We'll write it as 2k, and n will be our odd number, so it'll be 2 times L plus 1, because remember, these guys could be different, so I need to use different variables to express them. And I introduced k and L, so we'll say for some whole numbers, k and L. All right. Now, I want to write the product of these guys, so m times n. So that's going to be 2 times k times 2 times L plus 1. Now the question is, how should we simplify this? And that is a good question. And the thing with simplification is that it really depends what you want to do with it to determine the best way of simplifying it. We're not asked to do anything in particular, but let's say if we wanted to show that the product of an even number and an odd number is even. Then, how do we want to simplify that? Well, we know that an even number can always be written as 2 times some other number. So, could we simplify this expression here to look like 2 times some other number? So let's try. And in fact, this is kind of easy. So we have 2 times k times 2l plus 1. All we really need to do is we need to say, well, if I take 2l plus 1 and multiply it by k, that gives me a number. So let me just put brackets around that. So this is definitely in red here. This is a whole number. So it looks like I'm done. That's all I needed to do. I can write this as 2 times k times 2l plus 1. And so again, we've shown that the product of an even number and odd number is even. This is a little bit harder to show pictorially, but I think the idea algebraically is pretty good. So if we're ever able to write a number as 2 times some other whole number, and we note that, well, if we take 2 times a whole number plus 1, we still get a whole number. And then if we multiply that by a whole number, we still get a whole number. So everything is nice there. So this expression in red is indeed a whole number. So we are able to write m times n as 2 times a whole number. Whenever we can do that, that's a definition of a number being even. So we have shown that the product of an even number and an odd number is even. And we'll have a lot of practice with this stuff going forward. Let's do one more example on a new slide. We'll talk about consecutive numbers. So, here are 2 little problems, and I want you to show that the sum of 4 consecutive numbers is even, and the sum of 3 consecutive numbers has a factor of 3. So, let's do the first one, and then I'll get you guys to pause the video, try the second one, and then we'll go through it. So the first one, we need 4 consecutive numbers. So let's start with the smallest one. Well, examples of consecutive numbers. Again, examples aren't enough to prove things because you're only showing it for those particular cases. But let's say we have 7, 8, 9, and 10. They're 4 consecutive numbers. Well, another example, 21, 22, 23, 24. And you guys can check that if I do add up 7 plus 8 plus 9 plus 10, or 21 plus 22 plus 23 plus 24, or maybe 4 plus 5 plus 6 plus 7, I'll always end up with an even number. So a few examples can give you an idea of what's happening, but showing it in general gives you kind of a clue why this is the case. So we know what even number or what consecutive numbers are. So how are we going to write them? Well, whenever you're thinking of it, it's a good idea to say, well, how did I write down the numbers, for example, 7, 8, 9, 10? Well, all I did was I started with a number, let's call it n, and then get to the next number, I added 1. To get to the number after that, I added another 1. And to get to the number after that, I added another 1. So, my 4 consecutive numbers are going to be n plus 1, n plus 2, and n plus 3. And I bet I introduced the symbol n, so let me tell you that. Let n be a whole number. So n is some whole number, so I can write the sum of 4 consecutive numbers. Here are my consecutive numbers, n plus 1, n plus 2, n plus 3, and I want the sum of them, so I'm going to add them. And I do want to point out that these brackets aren't doing anything mathematically, but communicatively they are. They're kind of grouping together what are the separate numbers, n plus 1, n plus 2, n plus 3. So it's a good idea, if you're using them mathematically correctly, include brackets in places just to show what goes together conceptually, so when people are looking at your work, or when you're looking at your work even, it's a little bit easier to understand. So, we want to show that this sum is even. So, it's always a good idea, whenever you have these problems where you want to show something like this, write down what you want at the end. This is a little bit different than mathematics that you probably saw in high school, where you don't know the end and you just calculate, you know the steps to follow. Here you have to figure out the steps, but you know what you're looking for. I know that I want to show that this sum is even, so I should be able to write it as 2 times some whole number. So that's what I want to get. I should be able to write this sum somehow as 2 times some whole number. That's my goal, and I'm always keeping that goal in mind when I simplify things. Well, looking at this, it's hard to see immediately how I can write it as 2 times a whole number. So maybe let's combine our like terms and see how that looks. We have n plus n plus n plus n. So that is, let me use black here, 4n. And then I have 1 plus 2 plus 3 is 6. So remember, I know what form I want to get this in. I want to make it as 2 times some whole number. So I should be able to look for a factor of 2 because that's what I want. And I look, and both terms here have a factor of 2. So let's go ahead and do that. So we'll take out a factor of 2, and we're left with, well, if I take out a factor of 2 at a 4n, I'm left with 2n. And you can check if you did that correctly just by multiplying it back. 2 times 2n is 4n. And if I take out a factor of 2 from 6, I'm left with 3. And again, you can check 2 times 3 is 6. So it looks like I've done it. I've written this sum of 4 consecutive numbers as 2 times some other whole number. We'll talk a little bit more about this idea. It's called closure, where you can add and multiply whole numbers and still have another whole number. So that's a really important thing. We're not subtracting, so it'll never be negative. We're not dividing, so it'll never be a fraction or a decimal. We always stay with whole numbers if we're adding and multiplying. So that is great. But we've done it. We've written this sum as 2 times some whole number. So it looks like we have completed our task. So with number 2, I'll let you guys try this, but I'll just give you a little hint. So we want to show that it has a factor of 3. So rather than it being even, remember, even is just a way of saying it has a factor of 2. So if it has a factor of 3, I should be able to write it as 3 times some whole number. So pause the video now, try to write the sum of 3 consecutive numbers, and try to do the arithmetic to show that indeed you get a factor of 3 in the sum. Okay, so let's go ahead and do it. So let's let n be a whole number. Again, I'm introducing a variable. I better tell people what this variable stands for. Let's go ahead and do it. We need the sum of 3 consecutive whole numbers. There they are. And it's a good idea. I'm kind of telling you that this is true. But if you didn't know if it was true or not, if you were just exploring, do a few examples to convince yourself that this is an idea worth exploring. And if you do, you can check that the sum of any 3 consecutive numbers, you'll always get a factor of 3 in the sum. Okay, so let's do the same thing here. Let's combine our like terms. N plus n plus n is 3n, and 1 plus 2 is 3. And again, I'm looking to write this as 3 times some whole number. So I should be able to factor it at 3 at some point, and it's pretty immediate here. So I have 3n plus 3. They both obviously have a factor of 3. So I can write this as 3 times n plus 1, which is 3 times a whole number. A whole number plus 1 still gives me a whole number. So the sum of 3 consecutive numbers does indeed have a factor of 3.